Okay, so you should be done with your structural diagram now. And well, let's talk first about topography. So we're dealing here with quite high relief landscape. We're dealing with alpine type of relief. We have low elevations here, which are around 4,000 feet. And the highest summit, we can see that the topography rises very quickly if you look at how close the contours are. And we've got a series of ridges and valleys, and you can see a series of valleys running here in that direction, and a series of ridges, and then a big valley here and other ridges. The highest elevations are around 8,000 feet, so we're talking about 4,000 feet of relief. That's around 1,200 meter. That's quite high relief, but more importantly, if you look at the map, you can see very steep slopes. It's a very, very steep alpine landscape. In terms of the topography, what is interesting as well is that here we have a low topography. If you look at the contours, they're quite well spread out. You've got rivers, you've got little hills. It's sort of hummocky terrain. And then you get past this line, you get into the color, and the relief rises very quickly. So we've got a lot of relief here, highly dissected. But what is interesting to note as well is these yellow zones, which are low relief as well. And you can see that, okay, we've got steep, flat bottom, steep again. So we've got valleys here which are steep-sided and flat-bottomed. At the bottom of this valley, what we can see are these yellow units, which are Quaternary, Pleistocene and recent, and it says till, alluvium, colluvium, gravel. So, right, I guess it gives it away. These are glacial or fluvio-glacial sediment. These are landscapes that have been shaped by glaciers, and in that case you can see that the glaciers have been moving in that direction and then down across this structure here. Again, a glacial valley, which is very clear here, represented by this U-shaped, steep-sided, flat-bottomed valley. In terms of the structure, I hope you've all seen the thrust fault. So you can see there's very strong orientation of the structure, which are northwest, southeast. You've got a series of thrust, and you've got a series of units. And what you can see is that the thrust repeat these units. So we've got a repetition of a succession by a thrusting. What is interesting about this structure as well is if you look at all the thrust seems to indicate a thrust direction towards the northeast. So all the thrust seems to thrust in that direction. And what I'd like you to do before we go any further is think about, okay, if you had to draw a very schematic cross-section showing the thrust and these units, showing these beds, what would it look like? Before we do this exercise, let's think about the the succession itself. So we've got that quaternary that is here, and it's probably going to be, we don't have much indication of the thickness, but unlike the Triassic on the Bristol map, you can see that where these units are exposed, you don't see any of the underlying rocks poking through that sedimentary deposit. So we're probably dealing here with a quite consistent, extensive glacial valley fill, and in that case, we're gonna represent that valley fill in the cross section. It's probably a few tens of meters, potentially even hundreds of meters. It's very hard to tell without any additional information, but it's not that very thin sliver that of Triassic that we've seen on the Bristol map. What is underneath seems to be it is a sedimentary succession, and roughly, I mean, it starts in the Paleozoic, it starts in the Cambrian, and it's roughly continuous all the way from the Cambrian, Ordovician, Devonian, and then we get into the Carboniferous and Permian. You may notice one unconformity. The unconformity is represented here. You can see that we go from the Cambrian here to the Devonian, which means that the Cambrian Ordovician, the Silurian is missing. And actually, if you look at DCN, which is the base of the Devonian, so you can see DCN exposed here in grayish blue, and you can see that there are triple points at the bottom underneath the DCN layer. So here it's in contact with the blue ELX, then it's in contact with the orange EAR, and then here it's in contact with the light orange EPK. So we've got triple points, which means we've got an angular unconformity at the base of the DCN, but it's not a major unconformity. You can see that overall the contacts tend to follow each other. So there is evidence for erosion and an angular unconformity, but the angle between the beds is not going to be massive. As you can see, the beds, the contacts between the beds tend to follow each other quite closely. This is the only major unconformity, and otherwise, as we said, it's a sedimentary succession, bedded sedimentary succession. In terms of, there's a couple of mistakes that I'd like to highlight on this map. They are around this area, so let's zoom in. Here, so first mistake here, we've got EPK here, which appears yellow here. It shouldn't be yellow. EPK should be orange, like this one here. So you've got a bit of EPK which is orange here, and EPK that is yellow here should be orange. The other mistake is in the same area, and you can see that here you go from DPA, and then you get, okay, let's start on that side instead. Here we've got DPA, dark blue, and then we've got MBFL, which is purple, NBFM, pink, NBFU, gray. If we go on the other side of the valley, we've got DPA again, but instead of the purple MBFL, we have pink MBFU, which actually doesn't exist. If you look into the key, this unit doesn't exist. Then we get again into the pink MBFM and gray MBFU. So what we have here, that pink MBFU should be purple MBFL, as it is indicated here. So here on the line of section, this is not going to be MBFU, it's going to be MBFL. So on the southern side of this yellow, this is correct, this is not correct. So you're going to have to correct that. Okay, so these are the two corrections. We've identified the main units. We've identified that there's a series of thrust fault. What I'd like you to do now is think about, if you did a very schematic cross-section across that, try to represent the thrust fault and the beds, and more importantly, look at the dip of the beds and the dip of the thrust. And that's a very nice map to look at these things, because you can see how we have this beautiful V in the valleys, V on the ridges, that really give you the sense of the dip direction, and you can also calculate the dip angle if you really need to. You may have to do that when you build a cross section here. So have a think about that schematic cross section now.